Hi, I'm Juan Morales.
I'm Zachariah Rodriguez.
And I'm Kali Suzuki, and today we'll be talking about MPC for satellite rendezvous, object avoidance, and docking. So our project was motivated to modify existing rendezvous and docking trajectory, which uses MPC to include obstacle avoidance, because autonomous spacecraft should include this aspect due to space debris littering across space. Our controller should avoid this object and continue on the original or new calculated optimal path. So we use the continuous linear CWH equations to model our MPC. We want to obtain the relative motion to the target's reference frame for our controlled spacecraft with respect to the center of the Earth. And we chose zero order hold because we want to use a large time step, approximately 2 minutes, because in space it is important for fuel minimization and preservation as you traverse. So from using a zero order hold, we were able to get the closed loop solution shown here. We modeled it with 6 states, which are the position and velocity in each direction, and 3 inputs, modeled as a change in velocity or thrust in each direction. We also wanted to test how the dynamics served for an Euler versus zero order hold, just in case we could save some computational time by using Euler. However, we found that for a large time step, there was a significant model mismatch, which led us to stick with ZOH.
Okay, and for our MPC, we have two sections for the MPC. The first is going to be the rendezvous and the obstacle avoidance. On the right, you can see our setup, our cost function, and our constraints. And so for the obstacle avoidance, we simulate the object as a stationary box in 3D space. And you could see the cost for the object on the bottom, right above subject 2, where it has the lambda 1 transpose. We have some polytope matrices that represent the stationary box, A obj and B obj. And we weight this cost with the parameter lambda, which is approximately 4,000. And so we require that our satellite stays away from that defined box. And as far as the rendezvous phase, we use a reference governor-like approach, which is the XS in the constraints that you see down there. And we're also minimizing over that parameter. So we're basically calculating a new equilibrium point for every iteration of the MPC. And we approach that equilibrium point every time. And lastly, we have these thrust magnitude limits, which simply limit the amount that we change our XYZ direction. And for the second part of the MPC, we have our docking phase. Our docking phase begins when we reach within a 2-kilometer box of our target. Once we reach that, once we're within that box, we change from the previous cost a bit. We remove the equilibrium point, so the reference governor is no longer there. We add a terminal set equal to OINF derived from LQR. We also add an attitude constraint on the thrusters. And that's just a physical constant that's specific to the thrusters to not overwork them. And we modify the sampling time. We go from 120 seconds to 20 seconds. We do this because we need higher precision when we're closer to our object, as opposed to traversing a larger distance, like in the rendezvous phase. And so here is a plot of our trajectory with no obstacle. We have this initial point, and we use a prediction horizon of 20. The research paper initially suggested 30, but we reduced it to 20 to save on computation time. And the second plot is the plot of the obstacle avoidance. And so we've plotted both the original trajectory without obstacle avoidance and the trajectory with obstacle avoidance. And you could see on the bottom right plot, there's a close-up of the first top right plot. You can see that we're hitting it and we are avoiding it in the blue. Yeah.
So one proposed modification to our MPC was to use an obstacle constraint, just a state constraint to avoid the box altogether. This would be done with with an infinity norm of the constraints. So it would make sure that at least one of the box constraints was one of the box constraints was not met. And so what this did is it would, with the infinity norm, you'd be able to make sure that in each time step, you're violating at least one of the constraints that would keep the spacecraft in the box. So in order to do that, what we also had to do was we needed to simulate the system every second, because if we didn't simulate the system every second, then we would potentially miss out on when the spacecraft is inside our box or when it's near the box. And so what this did was, in each one of the constrained finite time optimal control problems, we needed to use 120 seconds, and we needed to at least 120 seconds, and we needed to sample every second. What this did was greatly increase the computational time. But that being said, this did make sure that we avoided the obstacle. Here in these plots, you can see that we do indeed avoid the obstacle, and we have a slightly different path. And the reason we have a slightly different path is because we used a 120 second constrained finite time optimal control problem, as opposed to the previous phase where we were able to do much longer because our sampling time was 120 seconds and we were doing 20 samples. So in this case, we're doing 120 samples, but our sampling time is 1 second, and so we're only able to do one of our impulses in this time. So we only do get to predict one optimal U, and so that changes the trajectory a little bit. There's a lot more further work that we can incorporate into this system. The longer prediction horizon is what I just talked about. The docking constraints, there are other docking constraints that are involved in actual satellite docking, and some of those are the line of sight constraint, in which the spacecraft needs to maintain within a line of sight of the satellite that it's docking with. The overshoot constraint, in which our spacecraft wouldn't be able to go past the satellite that it is approaching, and the thrust direction limits that make sure that our spacecraft doesn't shoot its thrusters into the satellite that it's approaching. These constraints were causing some issues in our model, and so we did not include them, but some further modifications could include them. Another really important improvement would be measuring the states and the obstacles, measuring the state and the obstacles for moving obstacles. If the obstacle was moving, then we need to measure the state of the obstacle as well. And we need to make sure that we know if it's going to come into our optimal path or not. And if it does, we avoid it. So that's a bit more complicated, and that can be included in further work. Thank you for listening to our presentation, and thank you for a great semester.